It's our next topic in calculus. So we're now on the final third of chapter 9. So the first third and the middle third was all about focusing on series tests for convergence or divergence. We're done learning those. The last part of the chapter does utilize some of those tests, but it definitely is not the focus. And you'll notice the last part of the chapter lends itself more to free response type questions as we start going through these. So our last quiz in this chapter will be more of a traditional quiz with the Flipgrid, and there's a little bit of Delta Math and a Google form. So this section is called Power Series. It's actually section 9.8. We are going to go back and do 9.7 after this one, but I felt like this one connects the most with what we just finished. So a power series is a series that is represented as a function of x. So we think of a power series as a function where it does have a variable. N is not a variable. If you wonder, you have n's everywhere. N is referred to as the index number. It's what's giving us our different term values. But you're going to have a variable, an x variable in, that's going to create a function-like series where you're going to have different values of x. Your x value will sometimes make it converge and sometimes make it diverge. There will be certain x values that will do one versus the other. And our job for a lot of this lesson is to figure out what x values would create a converging series versus what x values would create a diverging series. The basic form of a power series looks like what you see in front of you. It does always contain an x value. We also have what's called a constant or a c value. So that's going to be the center of the power series. So if you see like an x minus 5, that would tell you that the power series is centered at 5. If it's just an x without a plus or a minus, it is centered at 0, which is going to be the easiest. If it's x plus something, so if it's x plus 2, it would be centered at a negative value, so like at a negative 2. The domain of your power series are going to be all the x values that create a converging series. The way that we figure out when it will converge and when it won't is we use the ratio test. So since we just did the ratio test, I think it's best to go right into this section because you're now actually going to be utilizing the ratio test with pretty much every question in this particular topic. The ratio test is going to find those x values that create convergence. So we have a theorem, and it's basically breaking down the convergence of a power series into 3 different types. And so what I want to do in this video is definitely more of an intro video, is just kind of talk you through what are the options that happen so that when you come into class, we can actually get right to the problems and we don't have to spend time with all the beginning information. And that way we'll be able to do more practice problems and more AP problems when we're together. So for the A power series that is centered at C, one of the following types will happen. So your first type is that your series only converges where it's centered. So if it's centered at 5, it will only have a convergence happening when x is 5. When this happens, we say the radius of convergence. The radius is going to be how far out from the center does convergence happen. We would say the radius of convergence is 0 because we are only experiencing convergence at that center value. This is going to happen when you do a ratio test and you're going to get a divergent ratio test. Just to remind you how the ratio test worked, the ratio test was the one where you took the absolute value. If you got something bigger than 1, we said that it was a diverging series. And that's what's going to happen with this. You're going to do your ratio test and get a limit value that's bigger than 1. Your second type is going to be the most common type. The second type is when you have some sort of radius value that's going to be some number. It's going to be a positive number. And we can say that the series converges as long as it's within that radius, it's within that interval. So you'll go to the ratio test, and when you're kind of done with the ratio test, you're going to create this type of inequality. You're going to have just your x minus center left in absolute value. The absolute value comes from, there's an absolute value when you do the ratio test. And you're going to be less than some number. That number is going to be referred to as your radius of convergence. Essentially what happens, let's say you're centered at 3 and you have a radius of 2. What that means is your convergence goes out 2 units this way and 2 units this way. So we would actually create what's referred to as an interval of convergence, which I am going to define in a second. And that interval would run, in this case, if you go 2 units before 3 and 2 units after 3, you'd be looking at convergence that's happening from 1 to 5. So you're creating a region, an interval that is symmetric around the center. So wherever that center is, your radius of convergence is going to extend that many units on both sides, creating an interval where it would converge. This happens the most often. And again, this is going to come from the ratio test. You're going to get down to this. This is going to be our goal when we finish our ratio test, so we can establish how big is that radius? How far out does it extend? And then your third type is what would be a situation where your series is always going to converge, not only at the center, not only at a certain radius, but everywhere on a number line. We have a always converging series no matter what x is. This is going to be one where the ratio test would prove that it always converges, meaning you're going to get a limit that's always less than 1 no matter what x is. With this type of problem, we say that it has an infinite radius of convergence because it's extending in both directions infinitely. So our radius of convergence is infinite. Our interval of convergence, if we talk about that, would be something like this, from negative infinity to infinity, or we could say it converges for all real numbers. Every power series is going to meet one of these types. Either you're only going to converge at your center, you're always going to converge, or you're going to converge within a certain interval, having a radius that extends in each direction that same number of units. I would say if I had to break this down, you're going to see the middle type probably about 60% of the time, and then the other two types probably about 20% of the time. The other two types, the type 1 and type 3, will be much faster problems. They'll be the ones that you hope happen because they do end up having less work, but you're probably going to see more type 2 than anything else. So one more definition, and I know I've already referenced this multiple times, but I want to make sure you know what I'm talking about when I talk about an interval of convergence. An interval of convergence are all of your x values which would create a series that converges. So for example, if I'm centered at 3, so again, kind of think of a number line, and my radius is 4, that means I'm going to go 4 each direction. So my interval is going to go from -1 to +7. Now, once we establish that, and again, all of this is going to come from doing a ratio test, we also have to do something called checking endpoint convergence. And this is what makes that second type longer. Meaning I'm going to actually have to plug in and see when x is, for example, -1, what does it do? When x is 7, what does it do? So does it converge or diverge? So what you'll notice is you're going to have intervals that will look like this, that will have parentheses, meaning those endpoints do not converge. You're going to have intervals that look like this, where you have brackets, meaning those endpoints are converging spots. Or you're going to have a situation where one endpoint converges and one doesn't. So you're going to have something that looks like this when we set up the interval, that one of the x values when you plug it in will give you a converging series and one will give you a diverging. The way we check endpoint convergence is we are going to use one of the series tests that we learned in the first part of the chapter. So that's where those 10 tests come in. We use the ratio test for every single one to start, but we will use usually other tests. You'll see a lot of geometric, you'll see a lot of p-series to determine what's called endpoint convergence. So that's kind of the basics. I know it doesn't make complete sense until you actually get to see it in action, but if you can kind of go back and look at the 3 different things that could happen, the 3 different types, and can feel comfortable with that, then when you come into class, I'm going to go through 1 or 2 problems of every type before we jump into what the AP questions will look like.